with antimatter, supposedly, they have different charges. One is positive, the other one is negative. When they meet, kaboom, you have energy, I guess, whatever energy is. They disintegrate, they annihilate themselves, whatever that means. I guess they mean it turns into empty space. I don't know, you tell me, because I don't know what it converts to. They say it annihilates each other, whatever that means. They just say that the charges disappear, they neutralize each other. Well, I don't care about charges. I want to know what happens physically. If you have two little balls, right, and one is positive ball, and the other one negative ball, fine, whatever that means, I don't care. And they collide, and they annihilate each other. What do we have? What do they convert into? What do they morph into? Nothing. They say energy. Energy is a concept, so we don't know what they convert it into. So they don't have an answer for that. And that's part of the problem, okay? And here it is. This is the explanation, the AI overview, okay? Scientists have proven, they always prove, right? That there is more matter than antimatter by observing a slight asymmetry in the decay of certain particles, like beta mesons, at particle accelerators like CERN's Large Hadron Collider, etc., where particles can spontaneously transform into their antiparticles, but with a slightly higher probability for one direction. In other words, it's not symmetric. That's what they're going to say, okay? That's going to be their argument. Effectively creating a net excess of matter over time. This phenomenon is known as CP violation and is considered a key mechanism for the matter-antimatter imbalance in the universe. Their argument's going to be that you have matter, right? For example, an electron, right? Or, I don't know, a positive hydrogen atom or whatever. You got some matter and it meets antimatter, okay? One is positive, the other one is negative. They should annihilate each other. But what happens is there's, when they do these experiments, they find out that when they create one in one direction and they create the other one in the other direction, they realize that it's not symmetric, that the amounts are not always the same, and the matter always wins over antimatter, and that's why we have matter in the universe, meaning that's how the universe at Big Bang ended up with matter and not with non-matter. Because if they completely annihilate, there should be no matter whatsoever. Okay? But they say that there was an imbalance. There was a little more matter than antimatter, and when they collided, the leftover, the winners were the matter guys. Okay? So thank God we're here thanks to this matter thingy. Okay? What's the problem with all this? Well, there's just so many problems that's unbelievable. And a lot of it has to do with why quantum is totally irrational. There's nothing acceptable in science coming from quantum mechanics. Not a single theory passes the test of rationality. And they say, well, we know it's irrational. Well, if it's irrational, it doesn't belong in science. Science is only rational explanations. Okay? And that's where the problem is. Here's one example that puts us into the right focus on this. You have the positron, which in the 1930s was confirmed to exist. Positron is a positive electron. Remember, the electron is negative. Well, this is the same thing, the same exact electron, but it's a positive one. It's got to do, everything is the same. The weight, the mass, the size, whatever, it's all the same. The only difference is one is positive and the other one is negative. That's why they called it the positron, okay? And the guy who confirmed it was this fellow, and his name was Carl Anderson. And he ran an experiment in a closed chamber, vacuum chamber, right? When he opened it up, he found that one of the plates had this little streak, this curved line that you see there on the wafer, right? And he said, it should have, because of the magnets in the system, it should have gone the other way if it's an electron, but it went to the left, so I suppose, I think it came from the top downwards, I'm not sure exactly which, but the point is, it went towards the right when it should have gone to the left. That was the whole thing. And so they said, it's not an electron, it's a positron. And we discovered what other people predicted, okay? And one of the problems here is that you can see that the groove, the trench there, is not a solid line. It's got tiny interruptions. It's like little dots. So it's not like the little positron carved a groove completely in a curve, which is quite strange. strange because it was traveling at great speeds, and for it to turn that corner at such great speeds is already hard to believe. But the fact that it went jumping up and down like a jumping bean, right? That's already a problem because otherwise the groove would have been a solid groove, a single trench, continuous trench. That's not what we see here. We see up and down where some places it made the groove and some the dot, right? And some places it did not. How do we explain it with the rope model? Just to give it a whack with the rope, with many ropes going through that region, right? And that may have created that curve. But to say that that is a trace of a positron that carved a groove, a continuous groove, which is not continuous in this case, right? That's hard to believe. Here you can see the wafer in a little more detail, okay? That's what it looks like. That was the real picture of that groove, by the way. And you can see it's not a straight solid line, okay? So that's one issue, okay, that you got to think about. The fact that we're talking about a jumping bean, it went up and down, made a little dot, then went up again, made another dot. And, so not only was it curving at great speeds, because these things travel at the speed of light almost, but it went up and down while turning the corner. So if you can believe that, well, I don't know. Much easier to believe that, you get someone who jumps a rope, hits it in a single whack and makes that curve. That's much easier to believe that you have a particle making a jumping groove, trench, or whatever in the wafer. Okay, and so we question whether there are anything called particles out there. The quantum is par excellence, right? A particle theory. Quantum, that's what it means. A little small packet of something, right? And when you go to these accelerators, particle accelerators as they call them, you find this. You find these are pictures that they've taken from, what they do, their experiments. And they say pictures, the question, are these pictures? So the picture shows an electron with what? 16.9 mega electron volts initial energy, and it says it spirals about 36 times in the magnetic field. Well, I got a problem with that because they're taking a picture, a snapshot of a particle that's gone around 36 times, of something in motion. They're taking a picture of a movie. That's what you're staring at. They're saying, look, the electron made all these whirlwinds, whoop, 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 and we caught it in a single snapshot. All these curves that it made in just a short location, right? Because these things travel at the speed of light, and they're going around in circles. Why? Why are they going around in circles? Perfect circles almost, as you can see there. 36 of them all in a single snapshot. Is that believable? Okay. And this is part of the problem. These people are saying that they're staring at particles going around at great speeds, turning corners at great speeds, and that they took a snapshot of all these curves, of these traces, of these motions. We're not talking about a little dot. We're talking about an itinerary, a trajectory. And they took a snapshot of a trajectory. We're not talking about footprints, really. What we're talking about, the motion itself. They took a snapshot of the motion. Okay? And here you have a trace, a bunch of traces here, you can see. And they say all these traces are particles that are running around at great speeds and turning corners at great speeds, right? And the question is whether this is believable. And you're saying, well, they took a snapshot of this. Is that what they did? Well, actually, they did not. See, you get this one here, which is the famous one from the Brookhaven Institute. And they say, look, what we have here is two gold ions, beams of gold ions, right? And we crash the beams against each other. And the one you see on the left there, the famous one from the star system there, what we see there, supposedly, that's what you're staring at. All those lines that you see there, they are particles escaping ground zero. They all collided, and now they're all escaping almost in a straight line away from there. Not perfectly straight line, as you can see there. They're not perfectly straight. Some are slightly curved. But what they're saying is you've got an explosion there, a hand grenade exploding, right? Two particles or set of particles, gold atoms colliding, gold ions colliding, right? And they create all these particles running away from ground zero. And these particles, they say, are the quarks and gluons that make up the atom. That's what you're seeing there on the left. The one on the right shows what a quark-gluon soup looks like in their minds. They say, look, it's all these particles there, and you can see these little lines that connect them. Like, you know, what are those? And they say, those are bonds. You know, like James Bonds. They just put them in by hand. They say, look, all these particles are connected or whatever. And so the picture on the right doesn't match the picture on the left, but they say that we're looking at the same thing, a quark-gluon soup, essentially. Okay? And so the question, are we looking at traces of particles, or are we looking at, you know, you shake two atoms that look like the rope model, you know, all the threads, right, that are making the proton, for example. Maybe they're shaking that, and that vibration gets caught in the system that is used to detect that, right? And so they make an image. And so when you say, well, how did they come up with are they able to take a snapshot as soon as there's a collision? Is that how they did all this? And the answer is no. It's all done with computers. It's simulations. That's what it is. They just feed it into a computer, and here you see it, okay? Here you have particles move through the tracking device. Electrical signals are recorded and then translated to a computer model, okay? And so they're modeling all this stuff with computers. They're assuming they're accelerating particles to begin with. That's an assumption. But that's what they feed in the computer. They say, okay, we're feeding all this stuff as particles already. So we have these particles, this shower of particles from both ends colliding against each other, and we have this explosion. And do they take a snapshot? No, they don't. What they do is they simulate it with their computers, also the picture that they're going to end up with, and they're going to treat everything as a particle as if it were a done deal, because that's what quantum is all about. Why are they putting it as particles? Because they're worried about charge. They're worried about energy. They're worried about field. They're not worried about things. They're worried about mathematical concepts, and what they're illustrating is, with a computer simulation, right? They're simulating the physics. They're simulating their equations, their numbers in physical terms. They're replacing the values with a little ball. That's essentially the quantum ball. They have to put something there for people to more or less picture what's going on in there. And that's what you're seeing there. Okay, so this is the problem. The problem is there are no such things as particles to begin with. And a great part of that has to do with the fact that no one has ever, in quantum mechanics, or even before then, even in classical mechanics, all the way to the Greeks, and even before then, no one has ever produced the force of pull. You can't do pull with particles, with discrete particles. You need an elongated object that connects two objects. Then you can produce pull. But if you're going to try to produce pull with discrete particles, well, you're going to have a big problem. And so they invented all these mechanisms like Lesage mechanisms or Casimir effects, where they remove the particles between two objects and the particles on the outside push them together, more or less like that. It's the shadow mechanism, what they call. Why? Because it would be much easier to say, hey, let's produce pull. And in order to produce pull, you just put an elongated object between two surfaces, and now you have pull. But in order for that to happen, then they say, well, but I can't see or touch anything there. And that's when they screwed up, because there are objects that you cannot see or touch. And that's the one that they never figured out. If they would have pondered that possibility, we would have been done a long time ago. But since they could never imagine that there was an object that you could not see or touch, they never put anything between two atoms. And because they never put anything between two atoms, they never discovered the force of pull. And to this day, they're doing pull through push, or by cheating, as we'll find out here in a minute. And first, we got to show this before we get there. This is Arvin Ash, and he's saying, what is a particle? What is this quantum? What is this thingy that they call a particle? Well, it's a vibration, a local vibration of a field. Meaning that the particle, as you can see there, is not a discrete particle. It's not a quantum in the sense that it's an individual island. It's a peninsula. That's what it is. It's sticking out of the field, okay? And you have this for every particle known to man, known to quantum mechanics. So on top of the fact that they're saying they're accelerating all these particles, what are they accelerating? Not discrete particles. That's the way they illustrate it, as you just saw a minute ago. What they're really doing is showing this lump moving along the field. And I guess it never gets its independence from the field, because as you can see, it's part of the space-time of whatever particle that is. And that's a problem. They cannot conceptualize any of what they're doing. And they say, oh, we cannot conceptualize it. Then you don't have a theory. If you cannot conceptualize it, what are you trying to teach me? How the universe works when you cannot even picture it yourself? This is the problem. Yeah, quantum mechanics is absolute rubbish because it's based on particles. They should have abandoned the particle hypothesis, the quantum, a long time ago. And that's what they're doing now. They're replacing with quantum field theory, which is a field, an extended thing that extends throughout the universe. And they say, well, what is a particle in that context? Well, it's a local vibration of the field. What is a field? A bunch of numbers. What is a particle? A vibrating number. That's what it is. So now you understand. Okay, but how do they come up with all this stuff? I mean, they say they run experiments and they do calculations and so on. And so they say, we've proven it, we've demonstrated, give me my Nobel, that kind of thing. And here I'm going to give you an example first. This is dark matter example. It's outside of the subject matter today, but it's inside the subject matter only for the fact that I'm going to show you how they come up with these ideas. Okay, that's all I want to show you right now. Here's dark matter. How do they come up with dark matter? Does dark matter exist? Well, ask any mathematicians, they'll say that it does exist. They're looking for it with their telescopes. A lot of them don't believe in it. They're looking for alternatives, but most of them believe in dark matter. People won Nobel Prize, I think it was 2008. They won Nobel Prize for discovering dark matter, for proving the existence of dark matter. So don't tell me it doesn't exist. Yes, it does. They don't want a Nobel for it. So what is dark matter? Well, the way they came up with this, you can see it there, is you have this velocity. I'm not going to go through the little details of the equations here, but you have velocity squared, right? Just look at velocity. It's equal to gm, g being the gravitational constant, g, m, big mass, meaning the galaxy there. And you have the radius right at the bottom, little radius, meaning you have a radius that is smaller than the one at the bottom. That's all I'm going to show you here. We have distance from the center of the galaxy to that star there at the top, and the distance to another star, which is at the periphery of the galaxy, is longer. That's all I'm showing. So one has a little radius, the other one has a big radius, okay? So what happens? If you increase the radius, as you see at the bottom there, right? If you increase the radius, in order for the stars at the edge of the galaxy to travel at the same speed or faster than the ones on the inside, you would have to, if you increase the radius, it should go slower. And the only way you can compensate for that is by putting a fudge factor. It's called cheating, right? Fudge factor known as mass, kilograms, meaning dark matter. That's how they came up with dark matter. And it turns out this dark matter is invisible, intangible, it's translucent. You can see all the stars, you can see the galaxies in the background, right through it. It doesn't emit any radiation, so there's no way to capture it through gamma rays or X-rays or any kind of rays. It's not there. You're talking about Casper the Friendly Ghost. That's what you're talking about. You're talking about spirits. And so they have these dark spirits, and they say it's a lot of mass. They had to sprinkle it on the outside of the galaxy only in order to show why the stars on the outside go just as fast or faster than the ones on the inside. Because otherwise it's impossible. So they had to put all this dark matter, these kilograms by hand, just to make the equation come out right. So it was like a long shot, and that's what they're looking at. And they tell the astronomers, go look for it. Go look for dark matter. Yeah, because why? Because there's no other way to explain, according to them, why the stars on the outside travel faster than the ones on the inside. And that's what they see through their telescopes when they look at galaxies. They say, hey, that star on the outside, we calculated it's traveling faster than the one on the inside. How can that possibly be? Dark matter, dark kilograms. They put all these kilograms, they sprinkle them preferentially on the outside. We don't know why. I mean, why isn't this dark matter between the Earth and the moon? That's what you got to tell me. No, it's only on the outside. It affects only the stars on the outside. And again, it's a fudge factor they put in the equation so that they can explain why the stars on the outside travel faster than the ones on the inside. So this is a fudge factor. And so it's got nothing to do with physics. It's got to do with math. And they call that math dark matter. Here's the quarks. Do quarks exist like dark matter exists? Well, again, quarks have been proven to exist. We know for a fact that they exist. And it's like dark matter. It's just a calculation. There is no such thing as a quark or a gluon, no such monster. But how did they come up with it? How did they invent this? Why did they have to come up with this quark to explain something inside the atom? Well, the problem was that, like I explained earlier, protons, or the atom, the hydrogen atom, which weighs approximately or has approximately the same mass as a neutron, converts to a neutron every 15 minutes and vice versa. Neutron converts into an atom, free neutrons, right? So you have a hydrogen atom, it beta decays as it's called, into a neutron, and a neutron does the same thing after about 15 minutes back into an atom. And they say here it has charge, right? It emits radiation, etc., and here it doesn't have charge because the neutron is chargeless. What happened? How do we explain that? They turned on the light, thinking light, and they said quarks. That explains it all. And so that's how they came up with the quark. Here's the quarky, okay? What is it? They have these two up quarks and one down quark, and that's a proton, right? And a neutron is a reverse, one up quark and two down quarks, okay? And you say, okay, I don't understand anything. It looks the same to me, just the little D's and U's, and maybe the colors are different, but it looks all the same to me. Well, at least you can get the mass right, because those little balls look all the same size. So let's say that the mass passes the mass criterion. Yeah, it's got the same mass. Does it have the same charge? And that's where we have a difference. Okay, now we have something to look into. No, the D's and the U's are not the same when you come to charge, and that's the difference between them. All I want you to notice there is that the gluon bed springs that they have to put between them so that the U's and D's don't fly away. So the bed springs hold them together, and they vibrate, and it's like these bed springs go back and forth, like keeping them together. They always illustrate them like that. They also illustrate this, you can see a gray ball, circle really here, but it's like, you think of it in 3D, it's a ball that encapsulates the three quarks. And what is that gray stuff? I mean, what is it called? What should we call that? What is that surface? And of course they put it in there so that you say, well, I can see why the D's and U's, these quarks, don't fly away, because first they're held by the gluons, and then they've got this, this ball that encapsulates them, so I can see why they don't fly away, yeah. But what is that? They never identified these circles, these spheres that encapsulate the D's and the U's, the quarks. So all that you got to keep in mind, when you're going through this. Okay, and here you can see it in motion, and this is how they illustrate it. So what are those balls? The proton ball and the neutron ball that have those three quarks inside them. So you can see they don't leave the membrane. It's like they're trapped within the membrane. People say, well, I understand why, because there's this membrane that's holding them there. But they never identify that membrane. So we have no idea what that membrane is. Okay? So this is the issue. These are things that they never answer, they never explain, they never justify, and they just get away with murder because they illustrate them, but then they never define what they are, they never identify what they are. Okay, so here's bgaede's version of their protons and neutrons. Okay, here it is. Okay, they're talking about charge. Okay, let's talk about charge. Okay, everybody understands charge. So I put 2 visas and a MasterCard, and that's for the proton. And I've got 2 MasterCards and 1 visa for the neutron. And people might say, well, Bill, how do you know they're triangles and hearts? Oh, I mean, they put the ball in the previous examples by hand. I mean, I should be allowed a little artistic liberty here and put a triangle or a cone or a heart. Am I wrong? I mean, what kept them from putting a ball? I can put anything there because they never justified it. I'm not going to justify it either, other than artistic liberty. Okay. And you say, well, why Visa and why MasterCard? Well, let's explain that, okay? Here we have it, okay? We're going to explain that. We have in physics and chemistry, it is common to use elementary charge as a unit. Freestanding particles are integer multiples of elementary charge. Electric charge is quantized, right? And Faraday was the first to note that discrete nature of electric charge, meaning charge, right, has a certain value, okay? And that's going to be 1.6 times 10 to the minus 19 coulombs. That's the particle of charge, that's the ball of charge, that's the quantum of charge, okay? So it's quantized. Millikan's oil drop experiment measured the elementary charge, and he's the guy who measured it at 1.6 times 10 to the minus 19 coulombs, got a Nobel for that, okay? Has been discovered that quarks have fractional charges of either minus 1/3 or plus 2/3. How did they determine that? Did they go in there with their scopes or with some kind of electric device and measure that? No. They invented that. They simply got it out of their nose holes. Is that fair to say? So yeah, they got it out of their nose holes. Okay, that's how they came up with that. And you would say freestanding. See there, it says freestanding quarks have never been observed. So they never saw it outside of the atom, outside of the nucleus, right, of the neutrons or protons, and they just gave these quarks minus 1/3 or plus 2/3 values of charge. So we have a contradiction because we've already proven through all these people, Millikan, Faraday, etc., we've proven, right, that charge comes in a discrete unit, a quantum called 1.6 times 10 to the minus 19 coulombs. But they invented that quarks have either negative 1/3, the down quarks, and plus 2/3, the up quarks charge. So all you have to do is multiply negative 1/3 or positive 2/3 times the charge, 1.6 times 10 to the minus 19 coulombs, and now you know how much charge a quark has, even though there's never been one observed outside of the nucleus, meaning they have no clue whatsoever what they're saying. They just put them in there by hand like they did with dark matter. So if you just put it in there and say, well, I'm just going to give it that value, negative 1/3 for down, positive 2/3 for the up quark. Why did they do that? And now we come into why the neutron is neutral. And why they won Nobel Prizes for inventing the quark, okay? They had to come up with some kind of gimmick, some kind of accounting procedure. It's got nothing to do with physics. It's got to do with math. It's got to do with how do we account for charge, this 1.6 times 10 to the minus 19 coulombs that the proton has or the electron has, but the neutron has none of it. How did it disappear when it converts from an atom to a neutron to an atom? Why does it disappear when it goes to being a neutron? How do you account for that? Well, now you'll see the math behind this. Here you have it with my method, bgaede's method, using charge accounts, right? Everybody understands charge because everybody's in depth up to their necks, right? So let's say you have 2/3 positive charge. That means you have $66.66 in your Visa account. You can more or less understand because that's about as much as you do have in reality. But it turns out that in your MasterCard, you owe money. You overdrafted, you overdrawn, right? So you got negative 33.33. So what happens? If you look at the proton, it's got 2/3 plus minus 1/3, which is 2 Visas and 1 MasterCard. And so you have 66 plus 66. That's 133 rounding off. From that, you got to subtract 33 from the MasterCard that you owe, and it gives you 1. That means you have charge. But in the case of the neutron, it's the other way around. You have 2/3 plus 2/3, 1 Visa, right? That's where you have your $66, but you owe two negative 1/3, which is 2 33s. You have two Visa cards, two MasterCards, and you owe 33 in each one. Well, you're going to pull from the Visa your $66 to cover those two holes. What do you have? You have zero. That's why you have no charge. Okay, I hope you understood that. And so, yeah, now you can see why they had to invent the quark. So not only did they invent the dark matter out of thin air, simply because they needed the mass to explain what they were seeing there, which is the stars on the outside of a galaxy, the galaxy rotation problem, as it's called, going faster than the ones on the inside. But they had to explain also why the neutron, when it converts to a proton, acquires charge, and when it goes in the opposite direction, it loses charge. And for that, they had to cut charge, which is a quantum, which is a unit. They had to cut it in 3 parts. They gave it 2/3 to the positive, to the up quarks, and they gave a -1/3 to the bottom quark, to the down quark. And so now they were able to explain the conversion mathematically. So it's an accounting procedure. It's a mathematical gimmick. That's all it is. There are no such things as quarks inside the protons and neutrons, because protons and neutrons are not balls in the sense of, a sphere, which is what they always draw. And so the reason they cannot understand anything what they're saying, because they cannot illustrate what their math is telling them. Okay? And again, all these are just accounting procedures. That's all they are. They're just mathematical gimmicks, and that's what they get all those big Nobel Prizes for. Okay, so what's the issue? Well, the issue again is they say that when the universe expanded for the first time, you had more matter than antimatter. And the question is why? Why was there more of one than the other? Why should have been a tied game? They annihilated, no more matter of any kind, nothing there, whatever annihilation means, right? And so this is, here we have a couple explanations, right, of what happened there. Here you have a carbon and nitrogen, right? And the carbon essentially does a beta minus decay into nitrogen, antineutrino, and an electron. Okay, that's how they beta decay. It's called a minus beta decay because the electron is negative. And you have here another situation where you have a carbon 10. It decays positively plus-like, right, into boron, neutrino, and a positron. Okay, so this is just math. They needed to create this antineutrino and positron and all these other things that don't exist simply because these are accounting procedures. Okay, so what's the story? The story is that for some reason, these two processes are not symmetrical. Okay, you don't always get the same amounts if you use the beta minus decay as the beta plus decay. And so here's one fellow that explains it, more or less, okay, and let me get rid of this for a second here. And what happened was they ran an experiment called a T2K experiment. What did they try to do? What did they accomplish? Well, they sent a muon neutrinos and a muon antineutrino, whatever those are. Don't worry about it. Not important. Just labels. Determine how many changed into regular old electron neutrinos. Just your standard electron neutrinos. You know, everybody knows them. We eat them every morning in our soup, right? Results indicate CP violation. You know, matter antimatter asymmetry. Okay, so they should have expected the same thing, that quantities would be in equal amounts on both sides, whether they did one or they did the other, right? And it turns out that they found out that more neutrinos, muons, going to neutrino electrons than anti-neutrino muons going to anti-neutrino electrons. They found that one, you get more of those than the other, and so they suggest that this explains why we ended up with more matter in the universe than antimatter, why there's we have more charges than the opposite charges, whatever if you get a negative electron, why there are less positrons, right, and so on down the line. So this is how they explain the creation of matter. It's just math. And they say they did an experiment. They found out that this was the case, that there's a symmetry between these two processes, and that there's more of the matter type than the antimatter type. And that's all there is. And it's just, and there, the values there at the bottom, the one that's circled, right, in red, those are the ones that they try to test. So all this is just accounting. That's all it is. There's nothing more than accounting. They say that this proves, but of course they cannot picture it. They cannot make a movie of it for you because whatever they illustrate does not match, reality. They cannot put it into real terms. They can only express it to you mathematically, or say, this is how we inferred from math. These are the explanations we infer from our math. What is the math? Just accounting procedures, just mathematical gimmicks. And so, yeah, I like to put this lady again one more time. I think she says it the right way, and that's why we should listen to her very carefully of how much all these people know and where they're at today. What kind of progress we're making in physics. Listen to her.
You've been asking me for several years to talk about Stephen Wolfram's theory of everything. I haven't done that because I don't understand what he's doing. But recently I've realized that I don't know what I'm doing either. Indeed, when I look at my news feed, I don't think that anyone knows what they're doing.
Okay, so what's the answer? The answer is they have no clue what they're doing. All these mathematicians who call themselves physicists, they painted themselves into a corner. They've created all these concepts for which they've given Nobel Prizes in the past, so they can't pull those Nobel Prizes back out and say, well, dark matter doesn't really exist because we gave a Nobel Prize for that. And quarks cannot be said not to exist because we gave a Nobel Prize for that. We can't remove the gluons because we gave a Nobel Prize for that. And so they had created all these monsters, including the positrons, which goes all the way to the 30s. They can't pull that out and say, well, the positrons really doesn't exist. We hate to tell you, after 100 years, we know now that positrons don't exist. So why did you give them a Nobel Prize? Why did you prove, did you confirm that it exists, and now you're saying it doesn't? So they can't pull all that stuff back out, and now they're painted into a corner. The new generations have to live with this because they go through school, through their freshman and sophomore years, they gobble this stuff. They have to study, memorize it, and if they want jobs, they had better, pray to the catechism, memorize it properly. And so they all learn the same thing. And so there is no variation, but they cannot make any improvement on it because now they're stuck. They're painted themselves into a wall with all these concepts that they've created. And they have no explanations for it. They cannot make sense of it. And that's what Hossenfelder was talking about. She's saying, we don't know what we're doing. And I totally agree with it.